So I'm all set whenever I think this is the time.
So welcome to the invited talk by Professor Sebastian Sioba. The chair of this session is Dr. Indulal from St. Aloysius College, Edatwa, Kerala. And I invite Indulal to chair this session. Thank you.
Thank you very much. I am most privileged to introduce before the audience the speaker of today's session, Sebastian Sioba. He is a professor of the University of Delaware, USA, and he took his PhD from Queen's University, Canada, under the guideship of David Grigory, Ramurthy, and David Velo on eigenvalues, expanders, and gap between primes. He is in the editorial board of several journals, including Discrete Mathematics, Discrete Applied Mathematics, Linear Algebra Applications, and so on. And he's a reviewer to American Mathematical Society and MathSynet. He's serving as a referee for more than 56 journals and has published 57 research articles in highly esteemed journals like Discrete Mathematics, Discrete Applied Mathematics, Linear Algebra and Applications, Linear and Multilinear Algebra, and so on. Sebastian Sioba had given almost 149 invited talks around the globe. And we are very happy and we are most privileged to have him for this session. And Sebi all lovingly call him as Sebi. Sebi will talk on eigenvalues and linear programming bounds for graphs and hypergraphs. And
thank you very much. Very kind.
Sebi, sir.
Let me share my screen and put the view. Yeah, so thank you again. I'm very honored to give a talk in this conference honoring Ramanujan's 100th anniversary since his birthday. So I will talk about some topic in spectrograph theory and related to eigenvalues of graphs and what we call linear programming bounds for regular graphs and hypergraphs. So to do that, I will start for people who are perhaps less familiar with this topic. In graph theory, you want to study properties of graphs using various methods. Obviously, combinatorial methods are the first that come to mind, but you can try to use geometric or topological or probabilistic methods. Also, a very powerful method is using linear algebra. And to do that, you associate matrices to graphs, and you study various properties of these matrices, various invariants, such as eigenvalues. So there are many matrices that one can associate to a graph, but in this talk, I will focus on the adjacency matrix. So if you have a graph whose vertices are labeled in some order, then the adjacency matrix has the rows and the columns indexed by the vertices of the graph, and in the position xy, you put the number of edges between x and y. And I will focus on graphs that are undirected, and so these matrices are all real and symmetric, and therefore their eigenvalues are going to be real, and we order them usually lambda 1, lambda in decreasing order from lambda 1 to lambda n. So this is a simple example, this friendship graph with two triangles, and it has 5 vertices. The 5 by 5 matrix is over there, and its eigenvalues are below it. Now, spectral graph theory, what it does, in some sense, it's a kind of allows you to play, like a ping pong game between a couple of areas of mathematics. So you will try to look at the graph and say, well, if the graph has this combinatorial property, then what can I say about its eigenvalues? And also you can play the game the other way around. And if you can say, well, if I know something about the spectral properties of this graph, about the eigenvalues, then what can I say about its combinatorial structure? So here's some simple examples. If we have a regular graph, so a k regular graph is a graph in which each vertex has exactly k neighbors. And the graph is connected. So it means from every vertex, I can get to any other vertex by some path. Then all the eigenvalues are going to be between k and minus k. And moreover, k is the largest eigenvalue, and it has multiplicity 1. So there is a spectral gap between k and lambda 2, which is, we'll see, it's quite important in connectivity and in expansion properties of graphs. Also, so again, the property of the graph being k-regular and connected translates into having this spectral property of having k as the largest eigenvalue and lambda 2, and a spectral gap between the first and the second eigenvalue. And another example of such a resulting spectral graph theory is the second one, that if the graph is k-regular, then the graph is going to be bipartite if and only if minus k is an eigenvalue. And again, bipartite is a pure kind of, it's a combinatorial property, and lambda n equals minus k is an algebraic property, spectral property. So this is an example of this type of resulting spectral graph theory. And below I put two simple examples: the complete graph K5, which has eigenvalues 4, and I put the multiplicity as the exponent, with the multiplicity 1, and minus 1 on multiplicity 4. And K33, which is the complete bipartite graph with 3 vertices on each side, where you can see that minus 3 is an eigenvalue, as well as 3. Okay. Now, I won't define expanders in a formal way. I'll just say that the expanders are a class of graphs which satisfy 2 properties. The first property is sparse. So think about a family of 3 regular graphs whose number of vertices grows. So think about a 3 regular graph, maybe on a million vertices, 3 regular graph on a billion vertices, and so on. So that kind of, it's clear that these graphs are sparse. If you do the calculation, the number of edges is linear in the number of vertices, which for a connected graph is as good as it gets. And the second property of these graphs can be expressed in equivalent form in languages of 3 different areas of mathematics. And I put them there again in informal way. These can be formalized if you wish, but I won't do it today. They're highly connected, which this is in combinatorial meaning, which means they have no bottlenecks, or they have high expansion constant or expansion properties. So if you look at the graph on the left, so I have here 2 graphs on 4 regular graphs. The graph on the left, you can see several bottlenecks. Like bottlenecks means I can cut the graph into 2 relatively large pieces by removing a small number of edges, just 2 edges. And this property of having being highly connected is equivalent to the spectral property of having a large spectral gap, like k minus lambda 2. We'll see in a second how large can that be. So that's algebraic. And the third equivalent characterization of this property is that if you do a random walk, you start at a vertex, on one of these graphs, and then you pick a neighbor at random and you go there uniformly at random, and then you continue this walk, then you're gonna converge to the uniform stationary distribution very quickly after a small number of steps, which kind of informally means you're gonna get lost fairly quickly when you walk in expanders. Okay. Now, I haven't defined h of g, but this is kind of this expansion measure of a graph. It's and in the 80s, there's work of Alon Millman, Chigger, Tanner, Mohar, who proved that this expansion constant is bounded from below and from above by a quantity which involves k minus lambda 2. So the one consequence of these results is that if you want to construct a family of k regular graphs where this parameter that I haven't defined, h of g, is bounded away from 0, is equivalent to constructing a family of k regular graphs where the spectral gap between k and lambda 2 is bounded away from 0. So that's kind of the meaning. Now, if we fix the degree of regularity k, then the question becomes how small you want to make lambda 2 as small as possible. And the question is, okay, how small can you make lambda 2? And this was answered in mid-80s by Alon Bopana. There's later work of Ser and many other people in which they show that, so one way of phrasing this fact is that if I give you a possible valency k greater or equal to 3 and a number less than 2 square root of k minus 1, then there are actually finally many k-regular graphs with lambda 2 at most and most theta. And these led to, I'll mention in the next slide where this comes from, to the definition of what I call now Ramanujan, what are called Ramanujan graphs. So a connected k-regular graph is called Ramanujan if all its eigenvalues except k and possibly minus k if the graph is bipartite are in absolute value at most 2 square root of k minus 1. Now, so this definition of Ramanujan graphs comes from the paper of Lubotsky, Phillips, and Sarnak, which is called Ramanujan graphs. I think it's in 1988 in Combinatorica, in which they have explicit constructions of infinite family of k-regular Ramanujan graphs when k minus 1 is a prime. And in their work, it's a beautiful work. They use number theoretic results related to a conjecture of Ramanujan about the number of ways of writing a natural number as a sum of 4 squares of a certain type. And that, the work of Ramanujan, the conjecture of Ramanujan, who was solved so it's a number theory conjecture, was solved by Eichler and Igusa, plays an important role in this construction of these graphs. So this work was done independently by Margulis, and later on Morgenstern extended the construction to k minus 1 prime power. So for a long time, the question is, what happens when k minus 1 is not a prime power? Are there infinitely families of Ramanujan graphs? Can you construct them, and so on? And so an amazing result was obtained recently, about 5 years ago, by Marcus Spielmann and Srivastava, who showed that for any k, there exists an infinite family of k-regular graphs with lambda 2 at most 2 square root of k minus 1. So they use this theory of 2 covers of 2 lifts and sign adjacency matrices to be able to show this existence result of infinite family of k-regular graphs where they can bound the top part of the spectrum, the positive part of the spectrum. But they couldn't do it at the same time, both the top and the bottom part. But if you restrict yourself to bipartite graphs, if you do their work, if they, their procedure with taking successive 2 lifts of graphs, to bipartite graphs, then the spectrum always is symmetric with respect to 0. And so whatever happens on the positive side is going to happen in kind of mirror on the negative side. And they were able to prove this result, that there exists an infinite family of k-regular bipartite Ramanujan graphs. So again, an amazing result. Now, the thing that I want to talk to you about is what happens in this range when I give you k, I give you theta. What's the maximum order of this graph, vk, we call vk theta, of a k-regular graph with second eigenvalue at most theta. So various people studied related or similar versions of this problem. So there are some Japanese authors who study for bipartite graphs connection with design theory. Amit Hori and Lineal studied a different problem. They take give you the valency, they give you V, and they give you the girth, which graph minimizes the kind of this spectral second eigenvalues, let's say. There's a very nice survey by Krivelovich and Surakov called on pseudo-random graphs. So these are kind of graphs informally where I think Nogalon calls them ND lambda graphs or NK lambda graphs, k-regular graph on n vertices with lambda small, with second eigenvalue and absolute value small. And so there are various authors. Large part of our motivation came from a work of Ricci, Schutte, and Stover, who in 2013 have a result in which they studied this parameter using Serre's proof of the Alon-Bopana result. And I'll mention the results in a little bit. Similar problem was studied by Nozaki. You give V and K, and you want to find among all K regular graphs on V vertices, which one is the kind of best spectral expander, the one that has the smallest lambda 2. Okay, so what I'll give, it's a brief summary of some work we did so we have like 3 papers, mostly with Jacques Coulon and Hiroshi Nozaki. The first one is with my former PhD student, Jason Vermette. The second paper, we studied the bipartite version of this problem, and we have a recent preprint in our archive in which we study this version for regular hypergraphs. So I'll spend most of my time on the k-regular version and then mention a little bit about the other extension towards the end. So the key thing for our work, so again, the problem that we study is this parameter vk theta. I give you k, I gave you a theta, which is less than 2 square root of k, 2 square root k minus 1. What's the largest k regular graph that you can make, which has second eigenvalue at most theta? So in our work, a large part is played by this linear. This is we call a linear programming for graphs. It's Nozaki's theorem from 2015, and he gives an if you have a. So first, I'll tell you about these orthogonal polynomials, which are defined recursively as you see there, and they have the property that if each of these polynomial fa has degree I, it's a monic polynomial in X. And if you plug in the adjacency matrix in it, in the position AB, is going to give you the number of non-backtracking walks of length I from A to B. So it's an easy exercise to see that if you take the adjacency matrix and you raise it to the power I, in the position AB will give you the number of walks from A to B of length I. But these orthogonal polynomials give you the number of non-backtracking walks. And a walk is non-backtracking. Again, you go on edges, but when you traverse an edge, in the next step, you cannot go back on that edge that you just traversed. So you have to go somewhere else. Later on, after the next step, you can come back to that edge, but not just in the immediate step. So Nozaki result is that if you have a connected k regular graph with distinct eigenvalues theta 1, theta d, and if you have a polynomial of some degree, you can write it in as a linear combination of these orthogonal polynomials. But if you find a polynomial such that fk is positive and f of theta j are all non-positive, less or equal to 0, and all these coefficients are greater or equal to 0, then you get an upper bound on the number of vertices of the graph in terms of this fk and f0. It's not difficult to prove. Just uses spectral decomposition, like most of the results in spectral graph theory. And using these results, we can prove a general upper bound. So the general upper bound is as follows. You have our parameters k, and now we have two parameters t and c, and we have this t by t tri-diagonal matrix with the row sums are all k. And it's kind of like a quotient matrix. So it's kind of like you start with a vertex. It has k neighbors. Each vertex below it is going to have k minus 1 neighbors, and so on until you get to the bottom. And maybe at the bottom, each vertex has degree k minus c, and each vertex is going to have degree c up. So that's in the hypothetical situation that there is such a graph. But this matrix exists without having the need to have such a graph. So this matrix, you can make this matrix for any t, any k, and any c. And if you take theta to be its second eigenvalue, then we can prove that vk theta, this upper bound in terms of k and in terms of t. So this is a general upper bound, and again, so the quick idea of the proof is that this tri-diagonal matrix, you can go into it, and you can, I told you that the row sums are k, so k is going to be a largest eigenvalue, and you can do a little bit of work, and you can find its characteristic polynomial as being x minus k times something in terms of these polynomials fi, and then you just apply the Nozaki LP bound to the right polynomial, and the result follows. Now, okay, what are some of the consequences? So again, you can characterize equality case, and we'll have some of our extremal examples are going to be extremal examples where this equality happens. So vk theta is going to equal this upper bound when we have some kind of distance regular graph with this quotient matrix. The other thing that the behavior of this parameter theta, of course, depends on k, on t, and on c. And you can prove that it actually takes any value. Like if you change this value, it can, like, let's say we fix k, and then we can play around with t and c. It can take any values between -1 and 2 square root of k minus 1, which was again the bound coming from the Ramanujan graphs. And one consequence is you can get like another proof of the Allen-Bopana theorem. There's several proofs of it, Friedman, Alon, I gave one, Mohar, and so on. And so you can take this matrix, which is pretty much almost like would be like a T1 would be kind of like the quotient matrix of a tree, almost like a tree. The second eigenvalue of this matrix is 2 square root k minus 1 times some cosine, and this is explained in it's not very difficult, but it's in Bana-Ito's algebraic combinatorics book. And these values, as theta is less than 2 square root of k minus 1, then there's always some kind of tau such that theta is less than or equal than lambda 2 of tau. And this vk theta function, it's kind of monotone with this second parameter, and you get this upper bound right away. So basically, for any theta less than 2 square root of k minus 1, this is a proof that vk theta is actually finite. So you get this upper bound on vk theta. Yeah. So this is a little bit different because I think the usual proofs of Allen-Bopana theorem, they tell you that if you have a theta less than 2 square root of k minus 1, you get an upper bound on the diameter of the graph. And of course, if you have a k-regular graph with an upper bound on the diameter, then you should get an upper bound on the number of vertices. But this just skips the diameter. It just goes straight to the number of vertices. So in our work, we did, I'm sorry for putting so much information, but VK1, it is a bit of work, but it's not so hard because you solve it using the complement problem. And if second eigenvalue is at most, it's at most 1, then the smallest eigenvalue is at least -2, so it's not so hard. We have a bunch of nice graphs, all these geometries and so on that gives us equality. And we managed to prove and disprove some conjectures from the Ricci-Shuri paper, Stover paper, about like various parameters, V32 and V42 and so on. So the first statements are the same ones they made in their paper, and then we prove some to be true and some to be false. So I'll go quickly over to talk about the connection of our work with the degree diameter problem. So the degree diameter problem is I give you a valency and I give you a degree. What's the largest k-regular graph that I give you a diameter? What's the largest k-regular graph you can construct with that diameter? So if I give you a k-regular graph with diameter 2, it's easy to see that the largest number you can have is k squared plus 1. And this is the amazing result of Hoffman-Singleton from the 1960s, in which they prove that if this happens, if there is such a graph with these parameters, then k is 2, 3, 7, and 57. When k is 2, the graph is C5. When k is 3, the graph is Peterson graph. When k is 7, they constructed Hoffman-Singleton graph, which is a 7 regular graph on 50 vertices. And this is a sketch of a construction which is due to Neil Robertson, in which you can build a graph from some C5s joined in a clever way. And for k equals 57, it's not known if such a graph exists. Now, the more general problem, when you have a k-regular graph of diameter d, then always like the number of vertices is at most this 1 plus k neighbors, then k minus 1 neighbors at the next level, all the way to d minus 1. And Bana-Ito and Damerel, like Hoffman and Singleton before, they use all these results have linear algebraic proofs. They prove that when the diameter and k are both greater or equal to 3, there are no graphs that attain this Moore bound. Now, one thing, so in a recent paper by Diniz, Shapiro, and Shahaf, they show that if you have a connected k-regular graph of diameter d, and lambda is the second eigenvalue, then n is at most the value of this orthogonal polynomial at k minus the value of this polynomial at lambda. So if this lambda is large, then g lambda is positive. So you are actually, maybe you know that you are not going to get Moore bound for sure from Bana-Ito and Damerel, but you are actually able to shave off something more, okay? But their work doesn't say anything about what doesn't have a consequence if lambda would be small. So from our results, it follows that if lambda 2 is small, then you can also upper bound the number of vertices using the previous result, and you get an improvement, not necessarily in like some kind of additive term, but you can get something with in this kind of multiplicative term here, C. So we discussed this a bit more in the last paper. I'm not going to go too much into detail, but I'll give you an example of how would it work for numbers, for specific numbers. So here, if you have k equals 8 and diameter is 2, the Moore bound is 65. And it's known that the biggest graph that there is that is being constructed is 57. And the Moore second eigenvalue for this hypothetical Moore graph that it doesn't exist is 2.19. And from Dinitz, Shapiro, and Shahaf, if the second eigenvalue of a graph is bigger than 3.4 and so on, then this graph, 8 regular graph diameter 2, is going to have less than 52 vertices. And our result covers the lower part. So we can say, well, if the second eigenvalue is less than this value here on the left, then the graph has less than 57. So it kind of, in some sense, it narrows the possible values of the second eigenvalue for such for these graphs close to attaining the Moore bound. So in some cases, like the gaps is quite far. In some other cases, you know, you see like it's fairly close, like 3.5. You can get you know, fairly close intervals. Okay. Now, so I'm have a little bit more time. So I'll mention briefly the question about bipartite graphs and hypergraphs. So for bipartite graphs, we study the same problem as before, but now we restrict ourselves to bipartite graphs. So bipartite k-regular. And it's not the same parameter because, of course, bipartite is a subclass of general regular graphs. And as a simple example, you can see like B31 is 8. And this is attained by you take the complete bipartite graph K44 and you take away a perfect matching, but V31 is 10. This is a Peterson graph, which of course is not bipartite. And we prove a similar result, like we prove like a linear programming bound as Nozaki, and then we prove a similar upper bound as the one that I mentioned before. This is kind of the description of the result. And we prove when the equality happens, and we also show that the bipartite bound, it's always going to be less than or equal than the general bound. So this value here will always be less than or equal than what we get from the other bound. And we find some, again, like these geometric graphs that can get us close to the, you know, get us some extremal examples. For hypergraphs, the problem for hypergraphs, there are many ways that you study spectral graph theory for hypergraphs. So the one that we do here, we just look at the point graph of the hypergraph. So we have an U uniform R regular hypergraph. So we look at the graph in which the vertices are the vertices of the hypergraph adjacent if they're in the same hyperedge. And so this is the Allen-Bopana bound for this type of hypergraphs. And for any theta less than this value, we're interested in this parameter HRU theta, maximum order of a U uniform R regular graph lambda 2 less than theta. And again, this is not, we prove that this is not the same as the other problem. So there's small examples, 431, this is 15, this is 18, this is 21. And I'm not gonna give you the details, but again, we prove general upper bounds and LP bound generalizing Nozaki. And again, we show that our result implies this Allen-Bopana theorem for this type of hypergraphs obtained by Kequin Feng and Winnie Lee in mid-90s. There's some simple, even for small values that we don't know the exact value. So we did VK1 in our paper. It's 2K plus 2. But we don't know VK square root of 2. So for V3 square root of 2, that's 14, this incidence graph of Fano-plane, the Hewitt graph. And then VK square root of K, we don't know if for K greater or equal to 5. For some K3 and 4, there are some nice graphs with these parameters, like the Pappus graph and the odd graph. And 6.2, we also, like that's the smallest value for which we don't know the small value for which we don't know the exact value. Like the linear programming bound we have give us 47. The second subconstituent in Hoffman-Singleton, it's a distance regular graph and it has like 42 vertices, but we cannot, we don't know which way, what's the correct value. So anyway, I'll stop here. Thank you very much for your attention.
Thank you very much, sir. Any questions? Any questions for a fruitful discussion? Audience, please.
Audience can unmute and ask directly. Dilal, please start.
Okay.
Ask participants to ask directly by unmuting their.
So participants can ask questions unmuting by unmuting their mic. This was a wonderful lecture on the aspect of Ramanujan bounds and the spectral gap based upon the Ramanujan bound. And also it opens so many problems for further research. I think if any participants wish to ask a question, they can unmute their mic and ask directly. Okay. So we feel that nobody is asking any question.
Yeah, it's late or it's early. It's okay.
Sebi?
Okay.
Yes.
Okay.
Yeah, I have a quick question. So what about sharpness of these bounds, whatever you have established? Like, are they sharp?
Well, some of them we can characterize, like we say when equality happens, and there are some parameters for which we can find equality. I mean, there are some open problems, like for bipartite graphs that we don't know how to solve. The things are in the paper, but for each of them we can characterize the equality. There is, in order for these bounds to be attained, these general bounds, you have to have like this kind of distant regular kind of structure with that quotient matrix and so on. But yeah, it covers some, certain parameters and so on, but like you saw, like for many parameters we don't know. And again, like it gives you this kind of different view of these Alon-Bopana bounds, where you go again, like the work of Neely and so on was, if your second eigenvalue is less than 2 square root of it's small, then you can upper bound the diameter. But here we go directly to the number of vertices.
Okay, thank you.
Yeah, thanks.
Will you be able to share your presentation? Can you send it to me?
Yes, sure. I'll email you my slides for sure.
Fine, because there are people who are interested in spectral graph theory here.
Yeah, I'll be happy to. Thank you.
Okay. As there are no other questions, we congratulate and extend our thanks to the wonderful talk by Sebastian Sioba. Thank you, sir.
Thank you very much. See you later.
Thank you, Sebastian and Indulal. We move over to the next plenary talk by Professor Kannan Soundararajan at 1945.
Thank you.
In the plenary talk link, please. Thank you.